Welcome to Maths with Bob. Today we are looking at asymptotes, and in particular I'm going to have a look at what's called oblique asymptotes. Now you can see here I've got GeoGebra just on animation, and you can see here we have a normal, just a hyperbola, and you can see that we actually have, if you like, a vertical asymptote and a horizontal asymptote. And what are asymptotes? Well, they're basically just, well, lines that can be curves as well, but basically the original curve is going to approach this other curve. It can be a straight line or can be another curve. So what's happening is as x gets larger and larger, the y values approach this asymptote, if you like, from above and below in this particular case. And we also have this vertical asymptote, which is when the, if you like, the denominator of a rational function is undefined, or is actually, I should say, its x value creates a zero value there, and hence creates an undefined y value. And we can approach that from the left and right, and you can see here we're going up to positive infinity. If we approach it from, if you like, the left, and we approach it from the right, well, let's actually say that again. If you approach it from the right, you're going up to positive infinity, and if you approach it from the left, you are going down to negative infinity. This is the vertical asymptote. Okay, so we're going to be looking at these sorts of ideas very shortly. And first up, I'm going to actually create what's called a oblique asymptote. Now, oblique asymptote is just something which is basically, well, it's not horizontal. The actual horizontal asymptote actually has a sort of an incline, if you like. So let's actually do that. Okay, I've now actually changed my, if you like, horizontal asymptote to an oblique asymptote. It's now 1.4x. This is actually just the, if you like, the asymptote which the curve is approaching is in fact this straight line y equals 1.4x. So we're going to actually be looking at, because this is the effect of an oblique asymptote. You can see here that the curve is still approaching this line from above or below as we go to infinity. And we still have a vertical asymptote as well. And you can see the vertical asymptote, we are approaching it from the right, we go up to positive infinity, and the left, we go down to negative infinity. So we're going to be looking at some of these ideas of what's called asymptotic behaviour, I guess, in curves. And in particular, I want to have a look at what's called oblique asymptotes. Okay, well, here we have our first example, a nice simple one, y equals x plus 1 on x. Now, there are a couple of things we notice about this particular curve, okay? As x goes to infinity, 1 on x will get smaller and smaller, so we need to know some ideas of some limits. That limit as x goes to infinity of 1 on x will in fact go to now 0. Now, obviously, if I go to infinity from above, that means positive, well, I should say positive infinity, then 1 on x will be positive, actually, approaching 0 from the positive side. And as x goes to, say, negative infinity, 1 on x, okay, will be getting smaller and smaller negatively, and obviously approaches 0 from what's called the negative side. So sometimes I can write this, I abbreviate this, the limit as x goes to positive infinity of 1 on x will go to 0, and I'll have a little superscript here from the plus, which means from the positive side, from above, if you like. The limit as x goes to, say, negative infinity of 1 on x obviously approaches 0 from the negative side, or from below, if you like to think of it like that. Okay, so the first thing is 1 on x will actually shrink as x gets larger and larger, basically, and our, if you like, oblique asymptote becomes y equals 1 on x. That becomes the overriding factor in our curve. So if we wanted to sketch this, we could straight away, if you like, know that y equals x is an asymptote. Okay, yeah. This is the line y equals x. Okay. Now, where is the curve? Now, we've got a couple of options. So I'm approaching it from above as I go to infinity. So if I'm going off to positive infinity, I'm coming down onto it from above. So it's actually in here. So I guess I just put a little curve in there. And if I'm approaching negative infinity, I'm coming down to it, well, coming to this line y equals x from, if you like, from below. Actually in this little section in here. And hopefully we can see that this is actually the situation. Now, we're not sure that this is what happens at the moment. Okay? But as we take, let's actually have a look at some of the limits as x approaches 0. Of this particular curve. Okay, so the limit as x approaches 0. Now, we can approach 0 from above, let's put it a plus, which means from the right. What happens? Well, we end up getting x, okay, we have an x value, which is approaching 0, so we have an x, which is going to be approaching 0, and then we have a plus or 1 on x. Now, as x gets very, very small, this term actually is getting larger. So this is getting very, very big. So it's approaching infinity. Now, is it approaching infinity from above or below, or if you like, I should say perhaps positive, negative, or negative infinity? So let's think about this. X is getting small positively, a small positive number, like for instance, 0.01. Okay, 0.01 is 100th. So its reciprocal would be 100. So it's actually approaching positive infinity. And this is where you can see here, this line here is, if you like, I just say, put a little bit of an arrow on the end, indicate what I'm talking about. It's a bit hard to see. But that would be going towards positive infinity as x goes towards 0 from above. Now, how about the limit as x goes to 0 from below? Okay, we have x plus, again, well, I should say x, which is going to 0, but let's just write x there. So we're going to x plus 1 on x again. Okay, this would actually go to 0, yes. This is the bit we want to look at, this bit here. What happens here? Well, as x goes to 0, now we're going to do it from below. I seem to rub that out before, but as we approach 0 from below, that means, if you like, a small negative part, like minus 0.1, its reciprocal would be actually negative 100. So this is actually going to approach negative infinity. And if you look down here, actually, it's going down this way. So this is going down this way. This is where that is. So we can see that our hyperbola, if you like, is hyperbolic arms, I guess, are in those two situations or positions there. Let's try a different example. Okay, you can see here I've just changed that simple example to from a plus to a minus. And what impact does this have? Well, we can see that as x gets larger and larger, we still have an asymptote at y equals x, yes. Okay, let's put in our oblique asymptote, y equals x, if you like. Okay, here it is. Now, what impact has that negative sign had? Okay. Well, let's actually have a quick look. Obviously, as x goes to infinity, okay, the limit as x goes to, say, positive infinity, we end up getting, of minus 1 on x, we end up getting a very small negative value. Therefore, if you like, y, the function, would start to tend to what? Let's think about this, okay? So as x goes to positive infinity, our 1, so we get x, which is a major term, 1 on positive infinity, so we're subtracting something off from x. So it's actually going to x from below. So we're actually approaching y equals x from below instead of above in the previous example. Let's have a look. As x goes to, say, negative infinity, y would approach to a negative, and a negative makes a positive, so we're going to be coming down on top of this oblique asymptote y equals x from above. Okay, so let's think. Where would that be? Okay, so we're coming, if x goes to infinity, we're coming to y. So we're actually we're coming up here, in here somewhere. So we're actually coming up to the line y equals x, which we know this is the y equals x here. And we're coming up from underneath, if you like, from below, underneath. And in the other case, we're having it from above. So we're coming down. It's basically, as x goes to infinity, we're approaching this curve from below. Okay, so it's going to be, okay. Oh, actually, this is actually, as x goes to negative infinity, y is approaching x from above. So it's actually in here. So it's actually going there. So what about, now, what about as x goes to 0? Okay. towards 0. Okay, so we want the limit as x goes towards 0. Now, we're going to go from the positive side. Okay, we end up getting what? Okay, we have x minus 1 on x. Okay, well, as x goes to 0, this would go to what? 0, and this would go towards what? Minus 1 on a very large positive number. This would head off to what? Negative infinity. Okay, and as the limit as x goes to 0 from below, okay, what happens here? Well, we have, say, x, so I keep writing 0 there. It's actually, it will go to 0, but it's, say, x minus 1 on x, okay. Yes, this will go to 0, and this will go towards positive infinity. Now, how do I know that? If x is very small negative value, like say minus 0.1, its reciprocal is say negative 100, and the negative of negative 100 is 100, so it's actually getting bigger and bigger positive. So how are we going to fit that in? Well, you might be tempted when you see this curve to try and fit a hyperbolic arm in here, right? Okay, like in there, for instance. But obviously this is not fitting the information, okay? So what we have to do is we have to sort of just now try and fit what's happening. So the curve is actually going off down towards negative infinity. So it's basically going down here towards, and so this is, if you like, the y-axis. And this one's actually coming up here. So if you like, we have, if you like, the hyperbolic arms are now in much larger, if you like, sections of the number plane. Okay. Okay, well, after a while, we can actually see what the oblique asymptote is, and hopefully we can see it's y equals 2x plus 3, because 1 over 2x plus 3, as x gets larger and larger, will approach a small value, so you're adding a small value to the line y equals 2x plus 3. So 2x plus 3 is, in fact, going to be our oblique asymptote. And so if we want to sketch this, basically, let's actually do a quick sketch, okay? So y equals 2x plus 3, so it's going through 3, 1, 2, 3. Okay, it has a slope of 2. Let's actually just put this in. Okay. Okay, all right. So actually, the value here is actually minus 3 on 2, which in case we haven't worked out is actually our vertical asymptote. Okay, why is that a vertical asymptote? Well, 1 over 2x plus 3 is not defined when x is minus 1.5. If you like, you create a 0 value in the denominator, and hence we have an undefined value plus a defined value, which actually ends up being an undefined value. Okay, so we can just have a quick look. The limit as x goes to, say, positive infinity. Well, y would go to what? 2x plus 3, yes. From the positive side, if you like. I can put some brackets around here and indicate from above. Okay, the limit as x goes to, say, negative infinity, y will go to 2x plus 3. We're taking a small amount off from below. So let's have a look. So basically it's in here, okay, from above, and we hopefully can see that this is basically what's going to happen. Down in here, it's going to be coming basically where it's from below. Okay, yes, so it's going to be in here and down there. Okay, but as you can see here, we're not 100% sure yet, but we do know that these sections here and here are approaching our asymptote here. This is y equals 2x plus 3. This is our oblique asymptote. Okay, so let's actually have a quick look at when x goes to minus 1.5. Okay. Okay, so let's have a look at the limit as x goes to minus 3 on 2. Okay, now what would happen? Well, obviously, if you like, the 2x plus 3 would actually go to what? 0. Okay, that's going to go at 0. What about this bit, the 1 on 2x plus 3? What happens when it goes towards there? If it's approaching it, now let's actually approach it from above a bit more than minus 1.5, then the value in the denominator will be positive. So, and it's getting smaller and smaller, so it's going to be this bit here, 1 on 2x plus 3 is going to be heading off to positive infinity. So basically 0 plus positive infinity is a positive infinity, which is giving us, if you like, this bit here, which is going off to positive infinity here. Okay. Now, how did I work that out? Well, I am a little bit more than, if you like, minus 1.5. So the value of 2 times something more than minus 1.5 plus 3 is actually positive. It's getting smaller. Its reciprocal is getting larger positively. You might think of it like that. Okay, so let's try another one. Let's actually try the other side. Just take the limit as x goes to minus 3 on 2 from the negative side. Well, obviously, again, 2x plus 3 is going off to 0. This bit here, 1 on 2x plus 3, is in fact heading off to negative infinity because we are now a bit below, so that's going to create a negative value in the denominator there. And it's getting smaller and smaller, so 1 over a negative value getting smaller and smaller is something getting, well, bigger negatively, I guess you could say. It's getting down to negative infinity. So this is, if you like, this bit down here. Okay. Now, a lot of times this is involved in what's called rational functions, and sometimes the rational functions will need to be separated. You can see here it's much better to separate them like this. I'll just show you another one where you may need to separate them. Okay, let's just have a quick look at now, sometimes you may need to do polynomial long division in these rational functions, but a bit of an indicator of an oblique asymptote is that if the degree in the numerator is higher than the degree in the denominator. Someone asked me once, can we actually have curves which approach curves? Yes, you can actually have curves which approach, so you can have the asymptotic curves. Curves can be asymptotic to other curves, like y equals cos x or hyperbolic cosine x. Have a look at that function, if you like. It approaches e to the minus x on 2, and depending on which way you're going. But anyway, let's have a look at this one. Okay, so we could break this one up into, 36. We don't really need to do polynomial long division. Okay, and obviously assuming that x is not 0, we can actually divide through by x. So we get, what, 6 on x plus x on 6. Now, you can see here, this, once it's written like this, we can straight away see that we have y equals 1/6 of x is an oblique asymptote. This bit here, oblique asymptote is this one here, 1/6, y equals 1/6 x. We can see here, this one here is going to create problems when x is 0, so we actually have if you like, a vertical asymptote when x is 0. So we could sketch it quite easily just from just general knowledge now. Let's try and sketch it quickly. Okay, here we go. 1/6 x. Okay, so let's just, it's quite a, there we go, 1/6 x. Okay, x goes to infinity, it goes to it from above, yes, okay, x goes to 0, from above we go to 0, positive to infinity. Okay, so we're heading, so we've got something like this, basically, in here. Okay, that wasn't too bad. Okay, let's try another one quickly. Okay, well, let's have a quick look at this final example. Okay, again, you can see here I have had to do what's called polynomial long division to break this one up, and we can see here that, okay, the degree in the numerator is again larger than the degree in the denominator. It's a rational function, they're both polynomials, they have no common factors. We can see that, in fact, the 2x minus 8 is going to be our oblique asymptote, so we obviously suspect oblique asymptote if the degree in the numerator is higher. And we can see here we're going to have trouble, if you like, when x is equal to -4, because that's going to be a vertical asymptote. So we're going to have a situation where, okay, the oblique asymptote is this bit here, that is our oblique asymptote, y equals 2x minus 8. We're going to have a bit of trouble down here, yes, okay, when x plus 4 is actually equal to 0, when x is minus 4, okay, we're going to create what's called a vertical asymptote. Okay, so we can sketch this quickly now from just our general knowledge that, in fact, 2x minus 8, so that's actually, okay, goes through minus 8, going through an 8 minus 8 here, has a slope of 2, okay. Okay, let's have a look now. Can I move that across? Let's see if I can move that across a bit. This one across. Okay, let's actually move these across a little bit because we're going to run out of space here. Okay, all right. So where is our, if you like, vertical asymptote at -4? Okay, so it's going to be. Let's rescale this slightly. So let's say down here at -4. Okay, we should actually make these dotted, these asymptotes, -4. Let's actually just fix that up quickly. Okay, so let's actually just fix that up. This one should be dotted as well. Okay, so let's actually just make that roughly to scale. Okay, so the slope doesn't look quite right there, at -8. Okay, now where is our, if you like, our function going to exist? Well, as x goes to infinity, we know we're heading off to 2x minus 8 from above. We also know if, say, x is 0, we are cutting the y-axis at 3/4. So we hopefully can see that we're going to be in here. Okay, this is going to be, what, 3/4? Okay, you just substitute x as 0 in, you get the y value at 3/4. Now, just general knowledge, we can sort of work out our other arm is in fact down here. Okay, sometimes the graphs come and cut the x-axis, which sometimes we need to solve some sort of equations to find those values. But you can see here, just with just a little bit of general knowledge and taking a little bit of analysis of the curves, we can actually work out these graphs quite easily. Okay, well, thank you for watching, and bye for now.